Basically, we will continue our discussion about Lie group and Lie algebra. So let's just refresh your memory what we talked about last time. So last time we talked about Lie group, which is nothing but group plus manifold. So it's this Lie group is a group and it's also a manifold. So Lie algebra, whatever. So Lie algebra is a linear vector space with Lie bracket. And so the relation, they're very closely related. So because Lie group is a manifold, so it's something like this. You can draw the picture for this, for the Lie group. And there's a identity element. And of course, we can calculate the tangent space, tangent plane at this point identity. So this guy is a linear vector space, right? And at the same time, this manifold is also a group. So there's some group operation which will give us a Lie bracket, which is a commutator. So this linear vector space associated with this Lie bracket will give us the Lie algebra. So Lie algebra is nothing but the tangent space of this Lie group at the identity. Sorry, Lie algebra. So the dimension, whenever we say the dimension of the group, by the way, if we denote the Lie group as capital G, so we usually denote this Lie algebra as like this kind of a curly G. Okay. So the dimension of the Lie group corresponding to the number of free parameters of the group. For example, for SU2, if you remember, I think it's something like I actually quite didn't remember what's exactly form. But anyway, it can be parameterized by x1, x2, and x3 and x4, and they satisfy x1 squared plus x2 squared plus x3 squared plus 4 squared equal to 1. So in this case, the number of free parameters is 3. So meaning that the dimension of this guy is 3. By the way, as usual, just feel free to stop me if you have any questions. Okay. And okay, so basically it's equal to the number of free parameters. And of course, the dimension of this like Lie group equal to the dimension of the manifold of this Lie group manifold. And we also know that the dimension of an object must equal to the dimension of the tangent plane, right? So it's also equal to the dimension of this tangent plane. This tangent plane is a vector space, so we can talk about the dimension. Basically, it's just the number of bases. The dimension of this. Remember that this linear vector space is nothing but Lie algebra. So the Lie algebra has the same dimension as the Lie group. And we know for SU2, the Lie algebra is generated by Lx, Ly, and Lz. So there, the dimension of this Lie algebra is 3 because there's 3 independent generators. And this agrees with the dimension of this Lie group. Right, so this is something I didn't mention last time about the dimension of the Lie group and the Lie algebra. So any question about this?
Could you remind me why we have the constraint that the x1 through 4 squared is equal to 1?
I think it's because we want this to be unitary. Basically, S means the determinant of this guy is 1. So eventually you get this.
Okay.
Yeah. But you can look up online, or here's just an example. Okay, so the next thing I want to say is about the representation. Representation theory. So far we only talk about the group in a very abstract manner. It's like, okay, we have some elements, we have some operations that satisfy some roles, right? But as a physics student, we really need to think of every element as an operation acting on something. So a very natural thing is we can think of an element, any element in a group as an operation or some transformation acting on some space. So if this space is a vector space, then we call it a linear representation. If this space generally is a manifold, then we call it nonlinear representation. And for us, the most relevant representation is a linear representation. Basically, we consider an element in the group as a transformation acting on a vector space. Let's denote as V. And V is known as the representation space of this group G. And now, because your group element is acting on the vector space, assuming the dimension of this vector space is n, then this element will correspond to a d by d matrix, right? This is very natural. And in this case, we call the dimension of the representation is n dimension. The dimension of this representation is n, basically equal to the dimension of the vector space you're acting on. There's nothing, okay, so there's no relation between this representation dimension with the dimension of the group. They can be very different. Okay, so let me give you the rigorous definition, or okay, so about the representation. So representation you can think of as a map R from your group G to some general linear matrix, n by n matrix. So this just means this matrix is invertible. Basically, you can calculate inverse of this matrix. Or determinant of this guy is non-zero. It's the equivalent, right? And satisfy the roles like the map of the identity. Sorry, the identity maps onto the you know, one element, like the identity. Yeah, this is very natural. And another thing is it preserves the group multiplication. So we map G1, G2 onto G1 times R G2. So here becomes a group, sorry, so here this multiplication is a group multiplication, but here becomes the matrix multiplication. And another row is the inverse. It also preserves the inverse. The inverse of an element equal to the inverse of this matrix. Basically, it preserves the group structure. Remember, the group structure is like a G1, G2 is an element in the group, and the G inverse is also an element in the group. Basically, it preserves the group structure and also maps identity to the identity in the in this like n by n matrix. It's very natural definition. So okay, this is for mathematician, but for us, the most relevant vector space is a Hilbert space because all the physical states lives in the Hilbert space, right? So V is our Hilbert space. In this case, the R, originally we can map our group to a general linear n by n matrices. But now we can only map our group element to unitary n by n matrix because operation acting on the Hilbert space naturally is a unitary transformation, right? So this kind of a representation R is called unitary representation. So this is the most relevant one for us. It's because all of our physical states live in this Hilbert space, and we want all the operations. We want all the operations to be unitary. Okay, so is it clear so far? Yeah, so here I just kind of tell you some basics, like something you need to know. Yeah, some basics. And okay, so now the question is how to do the representation, how to find the representation of a group, how to find the unitary representation of a group. Okay, that's the question. How to find. I mean, if you take a group theory class, there will be a kind of a rigorous procedure you can follow to find the representation. But I don't want to do that. That's the task of the group theory class. What I want to tell you is something I think that's enough for physics students to understand like the group theory related concepts in physics class. Okay, so so to find the unitary, anyway, in general, to find the representation, remember a Lie group is always related with the generator, basically the Lie algebra. So let's take SU2 as an example. This is a very good example. And actually, okay, so you will say, if we know the representation of SU2 group, we almost can get like the representation of all the semi-simple Lie group. But okay, let's forget about that. Let's take this as an example. We know the Lie algebra has 3 independent generators, Lx, Ly, and Lz. And of course, you can write it as L plus L minus Lz. It doesn't matter. Right? It's just a linear mixing of Lx and Ly. And if we know how we represent, represent these generators in n by n form, then we know how to represent SU2. Because we just need to take an exponential. Remember? So generally speaking, it's something like I x mu L mu, something like this. So generators physically is corresponding to infinitesimal rotation of this group. So once you know the infinitesimal, you can made up of you can get the finite rotation by kind of repeating this kind of infinitesimal process, right? Physically makes sense, and mathematically it also works. So the question is, what's this guy in a matrix form? And minus and L. And actually, a more important question to ask is, what's the vector space, or what's the Hilbert space you're acting on? So what's the vector space? So to specify the vector space, the thing you need to do is to specify the basis. So what's the basis? Right. So as I will say, so basically to specify a representation, there are two things you need to know. One is the basis of the space you're acting on. And the second thing is, okay, the second one. Second thing is what's the generators looks like in that space. So it's an M by M matrix, generally speaking. And the second, this guy is equivalent to, let's assume the basis is let's say AI, I equal to 1 to n, assume the dimension is n. So the second thing is equivalent to say, we only need to know how the generators acting on the basis. If we know how the generators acting on the basis, we know the matrix form of the generators, right? For example, here, assuming this guy is equal to some, I don't know, let's say, what's the notation? Um, the ij and corresponding to this guy and aj, something like this. Then I know that I just use the broad to, right? Okay. And we get the element ji equal to dij, something like that. Anyway, did you understand what I'm saying? What I'm saying is the two things we need to know. One is the basis. Another thing is how the generators acting on the basis. Once we know those two, we know the representation. Is it clear?
So will we cover how to find those L mu with alpha cat and with a cat?
So how we find this thing?
Yeah.
It's determined by the structure of your Lie algebra.
Okay.
Yeah, as you will see. So whenever we see this kind of abstract procedures, you should always attach these procedures with some physical examples. And that will help you understand some abstract stuff, right? Okay. Also, I think I'm pretty sure when this kind of mathematicians invented this kind of procedures, they also get the intuition from examples and make them more abstract. Basically, throw away some information, related to the specific examples and get some more abstract, more general theorem. Okay, so let's take SU2 as an example. Let's look at one. What's the so-called spin zero representation corresponding to a scalar. So in this case, the vector space is L equal to 0, M equal to 0. This is a vector space. This is a one-dimensional vector space, and the basis is this. And we know L plus acting on this guy is 0, L minus acting on this guy is 0, and L z acting on this guy is also 0. And this tells us all the group elements. Oops. Remember, all the group elements equal to x mu and L mu. Now L mu are all 0, meaning that all the group elements map to an identity, right? So all the group elements equal originally G1, G2, whatever. Now, after this map, I become 1, 1, 1, things like that. This just tells us this SU2 group acting on this space trivially. It will leave the vector living in this vector space unchanged, right? Because identity acting on any vector is itself. You get what I'm saying? And there's a special name for this representation. It's called trivial representation. Because we just naively map all the elements to identity. Yeah. And the vector leaving this vector space is called scalar, because it's invariant under this rotation, right? So when we rotate the system, the vector in this space will rotate like this, like and this is the representation of the group element G acting, in this space. And we know this guy is 1. So 1 times the cat is also this guy. So it will not change under this rotation. So it's a scalar.
So by saying rotation, do you mean that SU2 is a group of rotation in 3D?
Yeah. I mean, it's a rotation, or it's a rotation in spin space or whatever.
So is there any special, to say like the rotation in 3D space or in spin space?
Okay, so if you specify the rotation is like in 3 space, then rigorously speaking is SO3 group. We will come to that later on. Like there's some subtleties.
Yeah, but I mean, so without, if we were saying, if we're speaking about the rotation without specifying this 3D space, then what's the definition of a rotation?
Okay, so so here what we are talking about is like some abstract wave function living in this space.
Uh-huh.
And in this case, the rotation, meaning that we are acting our group element on the vector space. So when we're acting our group element on some specific vector space, we are doing the representation. We need to represent our group element using some matrices.
Uh-huh. Yeah.
But in this case, it's a one-dimensional vector space corresponding to, so the group element in this case is a 1-by-1 matrix, which is just a number.
Uh-huh.
And in this specific situation, all group elements is 1 and acting on the vector space, one-dimensional vector space trivial.
So this is done by like getting that these 3 L's acting on this vector gives 0.
Yes.
But how to define these L's?
This L's?
Yeah.
L plus L minus LZ? Or what do you mean by how do we define the L's?
I remember we did these L's starting from the rotation, but now it seems that you're like getting the reaction to this rotation starting from this. Is it kind of a circuit?
Yeah, okay, so first we define this kind of group. So we know this is a group by some specific rotation. For example, for SO3, we know it's a rotation in 3 space, in 3-dimensional space, right? But once we have that group structure, we can forget about that. That's just an abstract group. Okay, so maybe we can talk about spin 1. You will see what I mean. So spin 1 representation is exactly what you are saying. Yeah, the representation space in this case is a 3-dimensional vector space, and it's just you can think of it as our space or it's a spin 1 space. And mathematically speaking, they're the same, right?
Uh-huh.
Okay, so in this case, you have L equal. Okay, so so this is okay. So the vector space. By the way, this is why we also call this representation as a defining representation. For SO3 group. Of course, this is where our intuition comes from for SO3, right? Because it's kind of a very natural, it's in 3D. In this case, the basis, you can think of this as L equal to 1 minus 1, so M equal to plus 1. You may wonder how I get this kind of a basis, like in this kind of LM form. That's you need to do some algebra, and I just ignore that because I think this is enough for physics class. And we know how L plus, L minus, LZ acting on this basis. And I think you did in last quarter. And how we get this, we can get this L plus, L minus, and LZ in the 3x3 matrix form. Right? Which is, okay, so I can write down. Okay, let's write in LX and LY form, LZ. Because later on, when I talk about tensor product, I want to use some expression of this. Okay, so let's denote as this. This one means spin 1. And 0, 0, 0, 0, some minus I here. And I minus I here. And minus I here. Something like that. Something like that, I think. Wait. No, I don't think. This sigma z should be a diagonal, right? Yeah, but anyway, I think you get what I'm saying here. Once we understand how these generators acting on the basis, we can figure out the matrix form of these generators. And we have this once we have this matrix form of the generators, we know how to generate finite rotations, right? Which is L, something like that. And there are many different ways to parameterize this group. We can use the honor angle. Honor angle is kind of a, I don't know, theta, phi, and phi, something like that, and the exponential ij L, L1z, and some theta angle, I don't know, minus I theta phi L Ly or y L or Lx, I think, but I know something like that, right? And you get the intuition how we rotate. And this is the spin 1 representation. And this is exactly how we rotate objects in the real space. And also, this is how we rotate the object in this spin 1 space. And the objects living in this spin 1 vector space is called spin 1 of like spin 1, or yeah, or a vector, just a vector. And another thing is spin 1/2 representation. In this case, your dimension is 2. The basis is R equal to 1/2, M equal to 1/2, R equal to 1/2, M equal to minus 1/2. And similarly, we know how to act or act L plus, L minus, LZ on those bases. So we can write down the form, which is just the Pauli matrices up to a factor 1/2. Oops, this is and then we, by the way, the objects living in this vectors, this 2-dimensional vector space, we call it a spinner. right? And they rotate, how we rotate vector in the spinor space in this two-dimensional space. We also know how to do it. It's just minus I x mu and something like that, right? So you can say different objects live in different representation space, and they respond differently under rotation. And how will they transform under rotation depends on the representation. And of course, this is because they live in different space. And yeah. And their group structure are the same. They're all kind of a rotational like operation. Is it clear what happened?
Yo, can I ask one question?
Sure, yeah.
To what extent does the sort of unitarity of SU2, to what extent is it inherent in the group? And to what extent does it come in through picking a unitary representation? And like, are there non-unitary representations of the same group? I'm just wondering like how fundamental is the unitarity?
Okay, so I think there is a theorem saying that any simple or semi-simple, any simple Lie group, for any simple Lie group, any finite representation group is equivalent to a unitary representation. Basically, there are many, okay, for example, there in 3 dimension, okay, in 3, so this is a 3-dimensional representation. By the way, SU2 is a simple Lie group. It's just very fundamental. So maybe there's some non-unitary representation, meaning that your metrics are not unitary, right? Some general metrics, but it's always equivalent to the unitary representation. When I say 2 representations are equivalent, I mean by changing the basis of the vector space, I can change all the matrices from this representation to another representation. Right. So, yeah. I'm not sure whether I answered your question. Right. The group, yeah, the group needs to be compact. Yeah, you're right. Something like that. I also didn't remember exactly. Yeah, if the Lie group is non-compact, then there's no finite dimension unitary representation. For example, the Lorentz group. Okay, some very useful theorems. Yeah, but for us, we just need to take it for granted. It's like somehow obvious. Okay, so another thing I want to talk about is a direct sum and direct and the tensor product of representations. So first, let's talk about the direct sum. Basically, I want to explain to you what do I mean by this. Whenever we write down something like this, we say, okay, we add 2 spin together, we get a spin 0 and spin 1. What do we mean by that in terms of representation theory? Okay, so the direct sum, so of 2 representations. Okay, let's say I have a representation which is a spin 1 half representation, and I have another representation, spin 1 representation. First, like what I said before, first you need to tell me what's the basis of this representation space. So in this case, the representation space, the basis for the representation space is just this guy, and this guy, this guy, this guy. So basically the representation space is the direct sum of those two representation space. So this corresponding to the V plus, sorry, the spin 1/2 representation, this corresponding spin 1 representation, right? Now you need to tell me what this guy is. This guy is nothing but L. Oops. Sigma x, Lx1, and similarly for Ly is y, y1, and similar for Lz. Something like that. Yeah, like this. So this is what we mean by a direct sum of two representation. Basically, just put those two representation together, and they transform separately. So if I have some physical state, and the initial state stay in this V1/2, like this spin 1 space, A, B, and then 0. Then under rotation, this guy will still stay in that subspace, right? It will not jump to this spin 1 space. They will not mix because the off diagonal elements here are always 0.
So is this when they talk about like multiple particle systems being interacting or not? This plays a role in that, right? Because if the state is written with basically a combination of the two subgroups, it gets affected by both. I'm sorry, I don't really have the words to describe this very well, but
right, something. Okay, so I would say in spirit they are similar. So what you are saying is like in a different context. Here, what I'm saying is under rotation, they rotate in their subspace without kind of jumping into other space. So what you are saying is like I have a Hamiltonian, and two particles are non-interacting, meaning that in that case, it's not rotating or not any transformation. In that case, it's a kind of evolving, right? Right. And if the one particle and another particle, they just evolve according to their within their own subspace without kind of a mixing together. Yeah, in spirit they're the same, but not that relevant for us. Yeah.
Okay.
Okay, so this is the direct sum. By the way, this representation obviously we call it reducible, completely reducible, because we can very easily separate them into two representations, right? Another thing is the direct tensor product of two representations. So here I'm telling you some this kind of concept using examples. If you're really interested in the general how we do it, and you can just pick up a random group theory book and take a note. For example, spin 1/2, tensor product spin 1/2. Right, in this case, similarly, you need to tell me what's the vector space. So what's the basis? So in this case, basis is, okay, so we denote the vector space as this. The basis, so the basis in the first spin 1/2 is up, down, right? This is also up, down. I just use a physical notation. And the basis in the in this representation space is the 1 tensor product 2, 1 tensor product down to up arrow, down arrow, 1 tensor product up arrow, down tensor product down down arrow. So in short, for short, we denote as like this, down up, down down, something like this. Meaning that whenever we have two spins, if the Hamiltonian is like a two spin acting interacting with each other, for example S1 dot S2, then the total Hilbert space actually lives in this representation, right? Sorry, the total Hilbert space is exactly the representation of this, of the spin 1/2 tensor cross spin 1/2. And so what's the, now you need to tell me what's Lx and what's Ly, Lz. So they are nothing but the tensor product of corresponding representations. So you know this is 2 sigma x, first one, and the Simpson Z and Z component. So it's a 4x4 matrix, 4x4 matrix, right? And now the point is this representation, this is also a representation. This representation is reducible. Reducible, I mean by changing the basis, I can block diagonalize my generators. So by changing the basis, this is my original basis. Now I change my basis, okay? I change it to the triplet and singlet. Up, down, pass, down, up. If I'm going too fast, just let me know. I just felt like it's useful to illustrate this kind of a abstract group theory concepts using the examples you're familiar with. You get another kind of understanding, another way to understand this kind of familiar concepts using the perspective of group theory. Okay, so this is my original basis. Now I just change my basis and reorder them. In this case, in this basis, my original Lx would become, I mean, what I'm doing here, you can do it rigorously by kind of find the transformation of the basis and acting on this kind of 4x4 matrices. But if you do it out, you would finally get a 1 x and a 1, sorry, and 0. Ly 1 0 and Lz 0.
What does the superscript 1 denote here?
Oh, 1 means the matrices here.
Okay.
Yeah, the representation of the generator in the spin 1 space. So you can say now naturally all the generators are already block diagonal, and meaning that we can read according to what I said before, like this kind of a direct sum. I can write this representation as another representation, the spin 1 representation, direct sum with your spin 0, right?
So, but what if I have a direct sum of spin 1/2 with spin 1/2? Is it still this representation of the same group?
Yes, yes, yes. This is still the representation of SU2, but it's a reducible representation. Just reducible, I mean, when you do some change of basis, I can block diagonalize them, like what we have here.
No, I was saying if it's a direct sum of 1/2 and 1/2 instead
yeah.
of a tensor product.
Sorry, can you repeat your question?
So what if I have a direct sum of 1/2 and 1/2? No, not the tensor product, yeah.
Uh-huh.
Is this representation of the same group?
Yes, just a two copy of the spin 1 representation. Yeah, definitely.
But this is already, you know, how do you call it, oxymmetric, right?
What's that?
This one is already, or what was it, block diagonalized, right?
Yeah, this is already block diagonalized. Of course, you construct this representation using the direct sum. So yeah. This just tells us this representation can be decomposed into 2 spin 1/2. And this is why we use this like the sum like this, because this represent. You can totally call this representation like as some R representation, but we realize that we can decompose this representation into 2 spin 1/2 representation. So we write this R representation as 1/2 plus 1/2. By the way, to verify this is a representation, we just need to show this satisfy the rows I wrote down here. And if I have 2 representation, D1 and D2, and naturally, if you put D1 here and D2 here, they form a representation. Yeah.
Is there a physical situation that corresponds to the direct sum of a 1/2 and a 1/2? Because if you have 2 spin 1/2 systems, that seems to call for the tensor product.
Right. Yeah, that's I don't think so. So whenever you put the for example, I mean there are many systems like made up of many spins, right? For example, n spins, n spin 1/2. Then the Hilbert space is like a spin 1/2 tensor product spin 1/2, and there are n of them, and it's what was tensor product. It's like whenever, so this is how we construct Hilbert space of some system, of some condensed matter system. So whenever you are given a system, the first question you should always ask is, what's the Hilbert space of this system? The second question you should ask is, what's the symmetry of this system? Something like that. And then you can ask more questions, more subtle questions. Right. So whenever you have some, so for example, I have some small Hilbert space H1, and here some small H subspace H2, and H3. Then the total Hilbert space is just a direct, tensor product of them.
So is it like the direct sum is like it describes one particle, but it could be in like 2 Hilbert spaces. So we discussed like the total state was the sum of the 2 total Hilbert spaces. Well, the tensor product is like there are two particles, like two things living in 2 different Hilbert spaces, and you're taking a combination of these, like the state of them.
Yeah, that's exactly. So you can say this is when we write it down like this. I'm pretty sure you're very familiar with this, like just adding two spin 1/2 together. So our starting point is there are two spin 1 objects. So eventually you get a kind of a something. Eventually you get a spin 1 object or spin 0 object.
And now what is the so what is the motivation of jumping from one representation to another? Does it give us advantage in, like, to conserve some, I don't know,
What's the
symmetries or something?
What's the advantage of what? Oh.
Of going from one representation to another, right? So why is it important that these are the same, representing the same group?
So, so why this is important that they represent the same group? Because for fixed, okay, maybe, and what I'm going to say can answer your question. That's the relation between the degeneracy and the symmetry, the representation of a symmetry group. Now, what I was talking about is all math. There's no physics, right? Even though I use some examples of physics, like what you're asking, why we do this? Then we need to come back to our physics, because physically it's very natural. Okay, so degeneracy. Degeneracy and symmetry group. Oh, okay. So time really goes fast, and by the way, if you have something to do, or you're free to go, but I will finish this and post online. And if you have nothing to do, and you can stay here and we can discuss. I want to finish this, and the next discussion I can do some problems. Yeah, problems is much easier, you know. I don't need to prepare anything. I just pick up some nice problems, and okay, basically because problems is much easier to do. For discussion, for this kind of a mini lecture stuff, I need to connect my thoughts and also my previous notes, and yeah. Okay, what's this? Okay, so let's look at this. Okay, the most common question you have in quantum mechanics is to solve this stationary Schrodinger equation, right? Solving this equation is equivalent to diagonalize this Hamiltonian, right? They're equivalent. And Hamiltonian is always a matrix, even though sometimes it's this kind of a form. You can understand this kind of operator as an infinite dimensional matrix. So basically, we want to diagonalize this Hamiltonian. So in general, there's no reason why the eigenvalue should be the same. Generally speaking, they must be different, right? So if my Hamiltonian, sorry, after this diagonalization, I get some subspace which has the same energy E. Let's assume the dimension of this is D, has dimension D. So this guy, I assume the corresponding eigenstate is psi 1. This guy is psi 2. This is psi D. And this, I call this subspace as H tilde, and EJ something. There must be some reason for that, right? It's not an accident. The reason is the Hamiltonian must have some group, must have some symmetry, and it form a group. And this subspace is nothing but the representation space of that group. Okay. By the way, so far so good. Like what I'm saying here is just some standard quantum mechanics, right? Diagonal is Hamiltonian, and generally the eigenvalue should not be the same. If they're the same, here I assume there's a subspace with dimension d, and then there must be some reason for that. So let's assume there's a group, which of course some, generally speaking, some elements, and we say this group is a symmetry for the system, meaning that all the group elements commute with our Hamiltonian, right? And okay, so another thing is, let's write down H acting on this A, E, psi A. So A psi A is a basis vector in this subspace. Then I act my group element, a random group element on this equation, because group elements commute with my Hamiltonian. So here, of course, commute because E is just a number. So we'll get another state, which also has the energy E, meaning that this state, so far we have no idea what this state is, but we know this guy is in this subspace because it has energy E. Generally speaking, we can write this state in a linear superposition of my bases.
And how do you know it's a distinct state? I mean, because G could be like identity and then nothing happens, right? It's not a new state.
Yes, then that, okay, the reason I know is okay, that's a very natural question to ask, because if this is an identity, then there's no reason why. Okay, so let's assume this, okay, a very good question. I mean, you should always ask this kind of questions when you're learning this stuff. Okay, maybe let me finish my logic here, then I come back to your question. Yeah. Actually, the logic is whenever you act your state, you get something, another state in this subspace, and generally speaking, you don't know what it is. So this guy, if equal to this guy, only for very special case. But generally speaking, we know this state has energy E, then it's a superposition of these spaces. This is very natural. What I'm saying is very general. Generally speaking, must be this. And then you realize that here, we already get a representation of this group, because what I'm doing here is, under the action of this G alpha, I map my state A to a new state, which is given by A, B, G alpha, psi B. Meaning that in this case, we are acting our operation, we are acting this kind of group elements on the subspace of this H tilde. And each group element is realized using this matrix DAB. Of course, your DAB can be equal set is 1, 1, 1, 1. For all the group element I map to 1, 1, 1, 1, 1. Then it's just like what is acting on this guy, you get itself. But generally speaking, it's not. So in this case, the subspace from a representation space of your group, of the symmetry group. So far, is it clear what I'm saying? Now I would say this representation is an irreducible representation, meaning that I rotate a vector in this vector space. Generally speaking, this vector would rotate to another state in this subspace. I will give you an example. Maybe this is kind of abstract. I will give you an example, a very short example. After that, we can finish this. A very short example. It's like Hamiltonian equal to J squared. J is a spin operator. So what's this guy is? This guy is, after we diagonalize this guy, we know this guy is, so it's a 0. J can be 0, J can be 1/2, or, okay, let's assume, okay, so yeah, it's like this, and it's 1, and then it's like 0, 0 plus 1. So, and also is this guy corresponding to 0, 0 state, and this H can be 1, 1 plus 1. Let's ignore the H bar. Oops. Sorry. Equals J square acting on J m equal to J plus 1. So this is the eigenvalue. One plus one plus 1. So this is a subspace. This is another subspace, degenerate subspace. This is another degenerate subspace. You can say each subspace corresponding to a representation of the symmetry group of this Hamiltonian. This Hamiltonian is invariant under rotation. Each subspace, this guy corresponding to the spin 0 representation, the basis is 0, 0, like what I said before. This guy corresponding to the spin 1/2 representation, and the basis is down, up, down, sorry, up, down. Yeah. This is a spin 1 representation. The basis is 1, 1, 1, 0, and 1 minus 1. And you can continue that. So the final conclusion I want to say is the degeneracy of some Hamiltonian is always equal to the dimension of the irreducible representation of the symmetry group. I think Yaroslav made this statement during his class, but without giving any explanation. I hope this helps. Yeah, also this is useful because whenever you have some very complicated Hamiltonian, and you have no idea what's the group, what's the symmetry group is associated with this Hamiltonian. But by doing some experiments, you find that there's some degenerate space, there's some another degenerate space. And we know this degenerate space must be some irreducible representation space of the symmetry group. That would give some hints to kind of guess what the symmetry group is. Did you get what I'm saying? So you can go from here to here. Basically, the degeneracy can be get from the experiments. And from the degeneracy, we can guess what is the symmetry group is. Because different groups may have different dimension of irreducible representations. If you are really familiar with, you should have somehow you can guess the correct result. And you can also go from the right-hand side to the left-hand side. Once you know the symmetry group, you can immediately say there must be some degenerate space because this group has the non-trivial irreducible representations. Like what I said here, like what this example. Yeah, this is what I want to say. And basically okay, so combined with last discussion, I go through some basics about Lie algebra, Lie group, and the relation. And this discussion, I go through some using some examples to illustrate the representation and the direct sum, direct tensor product, and also the relation between the representation and the degeneracy of a quantum problem. Yeah, that's it. Any questions? Okay, so let me stop.